So here's a quick review. We started talking about random processes, right? So like I said, just like a random variable is a mapping from an outcome of an experiment to the real number line, just like that random process is actually a mapping from the outcome of the outcome to a function or a signal, okay? And that gave rise to two interpretations of a random process. And we said, KG, so there's this one interpretation, which is point one here, this point here, we just says, KG, for some outcome zeta one, the random process is a deterministic signal. So if I fix what the outcome is, what I'm going to get is a signal, okay? So remember, we said the random process is can be defined as a two-dimensional function where one argument is time and the other is the outcome. Okay, so in that sense, if I fix the outcome, what I get is actually a function or a signal. On the other hand, the other one, which is actually going to be more useful as far as our discussions today is concerned, is that if I fix the time, and for that particular time, I just look at what the random process is, that random process is only a random variable. Why? Because at that particular time, the function can take on multiple or many real numbers. Okay, so therefore, if you fix t, if you fix time, the random process is nothing but a random variable. So that's something that that's gonna come in handy as far as discussions today are concerned. And then we talked about different examples. I'm not going to go through these examples again. Three examples in particular. This fourth example we did not discuss in the last class, but I added them in my notes. And we may be actually doing this today as well, right? So I'm not going to go into details right now. I'll come back to this in a bit, okay? I do want to mention the categories of random processes here, something which we forgot to discuss last time, which is just like a signal is either a continuous time signal or a discrete time signal, just like that, a random process can be a discrete time process or a continuous time process. So if it's a discrete time process, you have the time as a continuous variable, and if it's a discrete time process, you have time as a discrete variable. Okay. Now, on the other hand, there's an additional categorization, which is in terms of the amplitude, right? So the random process can not only be discrete or continuous in time, but it can also be discrete or continuous in amplitude, right? So which gives rise to four categories of random processes that we can come across, right? The first one is time is continuous, the amplitude is continuous, and I'm going to use notation x of t for that. And then what that means is for a fixed time t, x of t is going to be a continuous random variable, okay? And similarly, the other three categorizations. So time could be continuous, amplitude could be discrete. And then for a fixed time t, x of t is a discrete random variable, and so on and so forth. Okay, so there are four categorizations as we're going to come across in the examples that we're going to look at. Okay. What we want to do today is start talking about mathematical tools which could be used to characterize random processes, right? And the first one of the mathematical tools we're going to look at is to derive the first order distributions of a random process. What do I mean by a first order distribution? Anybody ventures to take a guess?
Derivative के terms में कह रहे हैं first order?
No, not necessarily. What is meant by first order distributions? Derivative?
Power sir, जिसमें power 1 होती है, जिसमें ये मतलब होता है first order.
Okay, so what I mean by first order distribution is rather something else. So like I said, yeah, let's say if it is a continuous time random process, okay? So x of t is continuous time. Let's say it's continuous time. Time random process. Right, so with continuous amplitudes, okay? Now, if I sample this continuous time process at a particular time t, what do I get? Ji Mohsin, if I sample this x of t at time t, right? What is that?
So the PDF.
Yeah.
The PDF of the random variable x at time t.
Okay, so x of t at fixed time t is what? Is actually a random variable, or in what type of a random variable is a continuous random variable, right? So if it is a continuous random variable, we know that a continuous random variable is completely characterized by its PDF. Okay? A single continuous random variable is completely characterized by its PDF. So the first order PDF for this will be what? I'm going to use the notation. The first order PDF will be, so f x of t x, which is a function, which is actually a function of two variables. The function of the variable x, which actually describes what the PDF looks like, as well as a function of time, because as time changes, the random variable changes as well, right? So x of t1 may not be the same random variable as x of t2. So x of t1 may have a different PDF than x of t2. So therefore, I need to have this function, this PDF as a function of time as well. So it's a two-dimensional function. Okay. So I would say this is the first order PDF characterization of this continuous random variable, which has continuous amplitudes, right? If this had discrete amplitudes, so what would I have had to use? So I would have had to describe a first order PMF. Okay. Similarly, if this was a discrete time process with continuous amplitudes, I would still need a PDF. Okay. But rather accept that the time is going to be discrete and so on and so forth. Okay. Let's try to do this with some examples, right? And this is actually a continuation of the examples that we did. So I'm going to start out with simple examples. I'm going to move on to and build up on top of it, right? So the first example I have for you is actually something we did last time, but let me do this nevertheless. And that is, KG, if I define the random process as being equal to a times sine omega naught t, right? Where omega naught is fixed, and if you recall, a was actually a uniform random variable in between 0 and 1. Okay. So for a fixed t, first of all, I mean, can you try to determine what category would this random processes be from, right? The time is what? Is the time continuous or discrete? G. Asif, is the time continuous or discrete?
Continuous.
Continuous. And what about the amplitude? So if I fix time t, any particular t, right? So sine omega naught t, therefore for that time t is a constant. Okay. I get a random variable. Is that random variable a continuous random variable or a discrete random variable?
Sir, I'm not sure about that.
Okay. Anybody else? Demosin.
So continuous random variable.
It's a continuous random variable, right? So if it's a continuous random variable, that means I will need the PDF to describe that random variable. Okay. So what would that PDF be? And we did this in the last class. Humaz, what would that PDF be? So x of t at any time t satisfies what type of a random variable would x of t be for some time t? So we did this in the last class. G. Shoaib.
Sir, time fix है या time fix नहीं कर रहा?
Time fixed है. So when I say at that time t, so that time t is fixed.
Okay, so हमारे पास at that जो time की जो value है वो sin omega naught t में put कर देंगे and that value basically.
Exactly. And then what is the randomness? Where does the randomness come from?
The randomness come from A.
Yeah. So what would x of t be? So x of t is then essentially a constant multiplied by uniform random variable, right?
Hmm.
So what is a PDF of a constant multiplied by uniform random variable?
That's a uniform distribution as well.
That's
या
still a
मैं
uniform distribution. From where to where?
Okay, zero. So it depends on the sign omega naught t
Exactly.
के sign. If it is greater than zero, then we
Yeah.
did last time as well कि वो uniform random variable होगा between zero and sin omega naught t, and otherwise.
Excellent. Right. So it's uniform between 0 and sine omega naught t if sine omega naught t is positive. So it really depends on what t is, and therefore what sine omega naught t is. Okay. Otherwise, it's a uniform random variable between what? Between sine omega naught t and 0 when sine omega naught t is negative. Right? And for the singular cases where sine omega naught t is 0, I mean, this still applies. I mean, this just then it's not a random variable anymore. We know that x of t is 0 in that case. Okay, and that's something we talked about in the last class. Okay, so this is what I meant by first order PDF. So when if I fix x of t, if I fix t, right? So if t is fixed, x of t is a continuous random variable, and I can describe what the PDF of that continuous random variable is through the information that's given to me. Okay, let's do another example. And this example is once again what we did last time. So this x of t was equal to 2 times bi minus 1 times sine omega naught t, right? So this was so the phase shift keying that I talked about, right? So where b1, b2, all the way up to infinity, right, are IID Bernoulli, right? With probability that bi equals plus 1, which is equal to the probability that bi equals minus 1, which is equal to half, right? So this is information that's given to you. I mean, we did not exactly have this information in the last class, but let's say this is something that's given to us. Okay. Now, x of t at any particular time t. Another assumption I want to make here is that okay, so I've missed out something. Here is this is equal to x of t equals this quantity as long as I times t, actually I minus 1 times t is less than capital T is less than IT, right? And let's assume that t equals 4 pi by omega naught, right? And I gave you a realization of this random variable. Let me do it nevertheless again, right? So this is one potential realization of the random variable, right? So there's sinusoids which are modulated with either a plus 1 or a minus 1. Okay, actually, in addition, so this was 0. Okay, this was 0, and this was plus 1, right? So this was given to us. So that 2 times bi minus 1 is either plus 1 or minus 1. Okay. So this is what it looked like, right? And it goes on the negative side, right? And let's just do 2, and this goes on the positive side, right? So this corresponds to b1 equals what? Equals 1. This corresponds to b2 equals 0, and this corresponds to b3 equals 1, right? So for these realization of the random variables b1, b2, b3, this is the realization that I get. Okay. Now my question here is, what kind of a random process is this? Is this a continuous time random process or a discrete time random process? Right? Is this continuous time or discrete time? So that's my question to you. GLE, is this continuous time or discrete time?
Continuous.
It's a continuous time. What about the amplitude? Is it a continuous amplitude? Okay, so let me rather say, okay, for a fixed t, for fixed time t, is x of t a discrete random variable or a continuous random variable? What's the answer to that? Ghazi?
For any fixed time,
For any
then
time,
it would be
yeah, कोई time fix कर दिया मैंने t पे.
so it would be discrete then,
Discrete. Okay. So why is it discrete?
because like because b आपका flip change bit change कर जाता है ना.
Okay,
So
got it. Right.
if
So
it's 1, it
because
will be
it's
some value.
exactly because it depended on b, and b could only take on plus 2 values, either a 0 or a 1. Okay, there are only 2 possible values. Okay, because of which, okay. Okay, so because of which, what can I say about the PD or PM? Because it's a discrete random variable, what can I say about the PMF of x of t? Right, so the first order PMF for any fixed time t, what can I say about that? What would that be? So what is the probability of x of t for a particular x, right? Which is defined as the probability that x of t for a time t is equal to some variable or some value x. Right? What is this function equal to? What are the 2 values that x can take? Ji Shoaib?
So if we just neglect the pathological case of 0, तो हमारे पास there'll be 1/2 at 1 and 1/2 at -1, and that's it.
Yeah, but x of t does not take +1 or -1. x of t plus
Yes.
-1 तो नहीं होता.
X of t, हाँ ठीक है. So फिर हमारे पास okay, b can either take +1 or -1, and that's multiplied by sin omega naught t.
Yes,
Isn't it?
exactly.
So हाँ, so हमारे पास जो है एम्पलीट्यूड जो है वो हमारे पास हाफ ही होगा 2 इम्पल्सेस पे, बट जो हमारे पास जो x एक्सिस पे है वो हमारे पास आएगा sin omega naught t and minus sin omega naught t.
Excellent, right? And the way one of the ways I can think about this is if I fix, for example, any point time on the x-axis here. So if this is time here, right? So if I fix any point here, let's say this is some point here, okay? I know that the random process could either take on this value here, which is this, or it could have been flipped, right? So it would have been a negative version of whatever this is. But that value, the maximum value that you can take, the plus minus value that you can take, that depends on what time is, because there's a sin omega naught t term there, right? So that depends on what this function is, sin omega naught t is, okay? So I can conclude, therefore, that this is equal to either half when x equals plus sin omega naught t, or half when x equals minus sin omega naught t. Right, and this does not include the pathological case when sin omega naught t is 0. That's when the probability is equal to 1. I'm just, let me just tend to ignore that. Okay, and a 0 otherwise, right? 0 otherwise. Right, so this is the PMF, the first order PMF of this random process. Okay, so either it's the random variable can take plus sin omega naught t value or a minus sin omega naught t value, and that's it. Those are the only 2 possible values. Okay, let me give you a third example. So this is example 3, and this is An example that we did not do in the last class. So this is relatively new. So this x of n is a random process, which is actually equal to x of n minus 1 plus wn, where w1, w2, all the way up to infinity are IID, right? Independent and identically distributed, and wi is Gaussian with a mean 0 and a variance sigma squared. And the additional information that we have is that x of 0 is actually equal to 0. Right, so it's actually an accumulator. This is it's like you have Gaussian realizations of a noise, and you have that input into what? Into an accumulator, into an IIR filter. Okay, all that does is whatever the inputs is just keeps on adding it. Okay, so this is a function 1 upon 1 minus z inverse. The impulse, the z transform, the transfer function is 1 upon 1 minus z inverse. Okay, now for those of you who have studied ESP, right? Can we try to identify what the first order description for this random variable will be, right? In order to do that, first off, is this a discrete time process or a continuous time process? What do you think? G. Mosen.
It's a discrete time.
Is a discrete time process. Okay. What about the amplitude? So if I fix x of n, if I fix n, right, the time index n for any particular n, is that a continuous random variable or is a discrete random variable? G. Mosen.
It's a continuous random variable because of wn. So the value, the random variable wn, because of that, because it takes continuous values.
The wn is a continuous, adding continuous random variables to on and on and on. So therefore, the sum should also be continuous, right? Now, can I write x of n as a function of w's only? Can anybody help me there, Maz? So I've given you the hint. This is an accumulator, right? Nazish?
So W's added रहेंगे from 1 to n because x of 0 is 0.
Right. So x of n, because x of 0 is 0, okay, from signals and from DSP, that's quite straightforward, that x of n is actually equal to the summation from I equals 1 all the way up to n wi, right? Because it's actually an accumulator, right? So because x of 1 is just w1, x of 2 is w1 plus x of 1, but the x of 1 is x of 2 is, so x of 2 is x of 1 plus w2, right? And x of 1 is w1, right? So okay, right. So x of 1 is just w1, right? Because x of 0 is 0, right? So x of 2 is x of 1 plus w2. So therefore, this is w1 plus w2. And x of 3 is x of 2 plus w3. But this is just w1 plus w2 plus w3 and on, right? So this is an accumulator, okay? So if x of n is a sum of w's, can you describe the first order PDF of x at a particular n? Josefa, what do you think?
Say at a particular n,
Yeah.
basically, since we're adding up continuous random variables, so and it's and
so let me help
those
you.
variables are,
Yes, all of the variables are.
those are normal variables. So basically, it's gonna be another, it's gonna, x of n at particular n is gonna have a normal distribution with mean 0, and the variance will be sigma square over n, if I remember correctly.
Sigma squared over n here, right? Because if you add two independent Gaussian random variables up, their variances add up.
Oh, okay.
Okay, so each one of the W's, W1 through Wn, are Gaussian with variance sigma squared. So that means they have the same identical variance. So the variance of x of n is just the sum of the variances of each one of the W's. And therefore that variance is n times sigma squared, right? So x of n, therefore, is Gaussian, is normal, with a mean 0, because all of the W's are 0 mean, and a variance equal to n times sigma squared.
Sir, just a question over here. I'm just confused. Like, I think in the previous lecture we did that for a sample when we were calculating the variance of a sample. Over there, we found out that the variance of the sample is going to be the variance of the distribution divided by n. So
because there was a multiplied by 1 upon n there, 1 upon n. There was
okay.
ठीक है, वहाँ पे, so this is not part of, so ये था.
Oh, okay.
Right, so it's actually n times sigma squared divided by n squared ho jata. That's why you have an n sigma squared by n. But this is not the case here.
Okay, sir.
This is just a sum.
Thank you.
Okay, so therefore I can say that the variance, the PDF of x of n at a particular n is equal to 1 upon root 2 pi n sigma squared e raised to power minus x squared by 2 times n times sigma squared. Right, so this is the first order PDF of this random process. Okay. Now, are there any questions here before I move on to a relatively more involved problem? Okay. So here's example number 4, and this may take up the entire remaining part of the class. And with this example, I actually wish to introduce something called a random telegraph signal or a telegraph process. Okay, here's how the random telegraph signal. G. Mohsen.
So could you scroll up for just 1 second?
Yes.
Okay, sir. I'm done.
So random telegraph signal. So random telegraph signal is characterized by some time intervals t's. Mohsen, do you still have a question? Okay.
Sorry, sir.
Right. So let T1, T2, dot, all the way up to infinity. That be a sequence, right? So that be a sequence of IID exponential random variables. So random variables with the PDF of each one of those t's, because they're identically distributed, so I just need one PDF to describe all of them. Okay, and that is described as an exponential distribution with a parameter lambda. So this is lambda e raised to power minus lambda s times u of s. Right. So each one of these time intervals are exponential time intervals. Okay. How is the random telegraph signal described? Random telegraph signal, as you can imagine, a telegraph kya hota tha? Telegraph is just it takes on either a value 0 or 1, on or off. Okay, on or off, right? The way the random telegraph signal is described is through the following. If I have that realization of T1 all the way up to T infinity, T1, T2, T3, T4, the x of t starts out at t equals 0. That's the first thing. Okay. So this is the time axis, right? And this is a potential realization of x of t, right? What happens is the random telegraph signal starts out at time t equals 0 and starts out at the off stage, okay? And it stays off. Stays off for how long? It stays off for a duration of t1 seconds, where t1 is actually random. So depending on what t1 is, it stays off or at 0 state for a duration equal to t1 seconds, where t1 is random. And then when t1 time has elapsed, what happens is it switches state, right? And then it switches to the on state or the 1 state. Okay? How long does it stay on for? It stays on for another duration, which is equal to t2 seconds, right? So it stays on for t2 seconds. So this is t1. And then when t2 has elapsed, when t2 time has elapsed, it turns off. Okay? And then it stays on for another time duration, which is random. And how much? So that's t3 seconds. And so on and so forth. Okay? So that's what the description of a random telegraph signal is. Right? Which is not necessarily uniform. Okay? So this is t3, this is t4, this is t5, and this is t6, and so on and so forth, all the way up to infinity. Okay? So this is what the description of a random telegraph signal. So this is just one realization. One realization of x of t, right? A few things we know. Okay, this always starts at 0, starts at time t equals 0, and the initial state is always x of 0 equals 0. Okay? And then afterwards, it keeps on switching between 0 and 1, depending on what the outcome of the experiment was. And what is that experiment? That experiment draws T1, T2, T3, T4, T5, and so on and so forth. Okay? Now we're required to find the first order. So first off, is this a continuous time process or a discrete time process?
Continuous time.
It's a continuous time process. And if I sample it at a particular time t, right, I get a random variable. Is that random variable a discrete random variable or a continuous random variable? Dishana?
Sir, I didn't get your question.
So if I sample this random process at time t equals t, if I fix t, I'm gonna get a random variable. Is that random variable continuous or discrete?
Sir, discrete.
The discrete random variable, and what are the two values it can take?
0 and 1.
0 and 1, right? So those are the only two values that I can take. So when I say first order distribution, when I say describe करनी है, what I need to describe is the PMF, right? So I just need to find out. So our objective is to do the following. Objective is determine the probability that x of t equals 1 and the probability that x of t equals 0. Right? And I know that these are the only two values that the random process can take. And since they sum up to 1, all I really need to do is just determine one of these. And that could be, for example, the probability that x of t equals 0. Right? So this is just therefore, because this is 1 minus the probability that x of t equals 0, that means okay, this is the only probability we need to find. Now, how do we do it? That's now a challenge. Okay, that we need to, that's a problem that we need to resolve, a problem that we need to solve. Okay. Before I start giving the solution, any ideas how we can go about this? Any rough guesses? Let's see. I mean, how do you think? If let's say if this was a problem in your final exam, जी शोएब.
So इसका एक सिंपल मतलब वो लग रहा था एट जीरो, सो हमारे पास द पीएमएफ विल बी मतलब पीएमएफ की जो वैल्यू एट जीरो होगी, देन एट टाइम t is equals to t1 it will be the CDF evaluated at capital T1, capital T2 पे CDF evaluated at capital T2 and so on.
लेकिन शोएब देखिए, so the T1 and T2, all of these are random. Okay, so this T1 could be long, could be short.
Okay.
And how, I mean, and there's a certain PDF that describes how long or how long, statistically speaking, T1 and T2 could be. Okay.
Okay.
So I need to, so when I say x of t equals 0, what I really should look towards is trying to map this x of t being equal to 0 to some event on all of those t's, t1, t2, or t3, all of that. Okay? So कोई ना कोई mapping of events है, as always, as we always do in transformation of random variables, going from one set of random variables to another outcome, we just need to find an equivalent mapping. Okay? So we need to see when is x of t equals 0? What are the values or of t's that would ensure that x of t equals 0? Okay? What is the set of outcomes on t's? T1s through T1, T2, T3, and all the way up to T infinity that ensure that x of t equals 0. Okay? That's where we should be headed towards, right? But there are, I mean, that itself is really becomes very complicated. So I'm going to divide this into smaller steps. Okay? Multiple intermediate events, if you will. Okay? So I'm just going to give you a quick rundown before we break, and then we're going to come back, which is, okay, I am going to map this x of t equals 0 to the event that there are even number of switches in the interval 0 to t. Okay, because whenever there are even number of flips, that's when the telegraph signal comes back to 0. Okay, when there are odd number of flips, the telegraph starts at 0, and therefore, if there are odd number of flips, it goes back to 1. Okay, it goes to 1, not back, right? It goes to 1. Okay, but if there are even number of flips, it starts at 0 and comes back to 0 as well, right? So therefore, if we can find the probability that there are even number of flips within a certain time interval, that will give us a probability that x of t equals 0. Okay, and that's the first step. Okay, and then we build on top of that. Okay, how do I then determine what is the probability that there are even number of flips in a certain time interval? Okay, that's what our I mean, that's how we're going to proceed with solving this first order PDF. Okay, with this, any questions here before we break for 5 minutes? Okay, no questions. Right, so we're going to break. So the process that we're going to follow is, as I said, okay, I'm going to map this to intermediate events. I'm going to say that the probability that x of t equals 0 is actually equal to the probability that there were even number of flips. I'm not sure exactly what, but I'm just saying as long as it's even. If it's 0, 2, 4, 6, 8, or and so on and so forth, even number of flips in the interval. What interval? In the interval 0 to t. Right? If in the interval 0 to t, there are even number of flips, then I'm guaranteed that x of t at that particular time t is going to be 0. Okay? And there's a two-way implication. X of t equals 0 if and only if. So I would rather say x of t equals 0 if and only if there are even number of flips in the interval 0 to t. Okay? Does that make sense? I mean, this is just a mapping of events. Maz?
Yes, sir.
Right? And if there were odd number of flips, by the way, the pip, what would that be equivalent to?
1 होगा.
That would be equivalent to the probability that x of t equals 1. Okay, because it started out with 0. Okay, so the assumption once again is that it starts out with 0. That's the key. In the fact key, the even number of flips map to x of t equals 0. Okay, otherwise it would have been the other way around, right? Okay. Now the probability. So therefore, अगर मैं ये निकालूं किसी तरीके से, if I can just compute this somehow, right? That would be enough for me to derive the PMF, right? So this is what I'm gonna from here on try to derive. Okay. Now, in order to derive this, the probability that there are even number of flips in 0 to t, what I need is I need the PMF on the number of flips in the interval 0 to t. Okay. So what I mean by that is that the probability of even number of flips in this interval is actually equal to what? Is actually equal to a summation from n minus infinity to infinity plus infinity only over the indices n. And what do I sum? I sum that the probability that there are n flips in the interval 0 to t. Right? So if I have the PMF on the number of flips in a certain time interval, if I have that somehow, and if I sum that PMF over only the even indices, that will give me the probability that there are even number of flips in that given time interval, right? So from here, this is once again an intermediate step. From here, what I then conclude is, I somehow then need to compute this thing here, right? The probability that there are exactly n flips in a certain time interval. Okay, the probability that there are exactly n flips in a certain time interval. Okay, now, so therefore, what I'm once again saying is that this is what we need to compute. What is the probability that there are exactly n flips in this interval 0 to t? This is what we need to determine. Okay. Now, let me define some notation here. The first notation I defined for you, oops. Okay, so the first notation I have for you is that of something called Sn. And Sn is simply an accumulation. Sn is equal to T1 plus T2 plus T3 all the way up to plus Tn. Okay. So this is an accumulation of T1, T2, T3, and all the way up to Tn. And what does this represent? This is the time it takes to do what? The time at which the nth flip occurs. Okay. So this is just a sum. So for example, if you just go back and see and look at this realization of the random process, right? If I add T1 and T2, what do I get? So T1 plus T2, which is equal to S2, is exactly that time at which, so this is S1. So this is S1, this is S2, this is S3, and so on and so forth. This is S4, this is S5, and this is S6, right? And S6 is really therefore T1 plus T2 plus T3 plus T4 plus T5 plus T6. And it is exactly the time at which the sixth flip occurs. Okay, it's exactly the time at which the sixth flip occurs. Okay, and of course this is random because it's a sum of random variables, and therefore S6 is also random. And generalization kya hai? Sn is equal to the summation of T1 all the way up to Tn, and this is the time at which the nth flip occurs, right? Okay, So if I am given this new notation or new random variable, the probability that there are exactly n switches in the interval 0 to t, this is equal to, I claim that the probability, अगर 0 to t के दरमियान में सिर्फ n flips हुए थे, right? Can I describe that as in terms of an event on Sn and something else? Ji Mohsin?
Sir, then T would have to be between Sn and Sn plus 1.
Good, excellent. Mohsin, have you read about this somewhere else, or is this something you came up right now?
No, sir, it makes sense.
Yeah, excellent. So this is really Sn. That means the time of the nth flip and the time of the n plus 1. So time t से पहले होना चाहिए n flip का time, और time t के बाद होना चाहिए n plus 1 flip का time, right? So therefore Sn must be less than t, must be less than Sn plus 1. And there's an if and only if here, right? So there are exactly n switches in this interval. If and only if this condition is satisfied, S sub n being less than t, being less than S sub n plus 1. Okay? So this is what we need to find. And that's all we need to do. So that's, we're reducing it to smaller and smaller and smaller problems. Now our objective, therefore, is to try to evaluate what this is. Right? What is the probability that Sn is less than t is less than Sn plus 1? Right? And for this, I am going to follow an approach which is slightly different than what's there in the textbook. So this is one of the examples in the textbook, by the way. Okay, the way the textbook solved this problem is in a slightly different fashion. I'm going to do it rather differently in the sense that I'm going to go back to that talking about when we talked about two random variables and a joint PDF of two random variables. Okay, so when I say I need to find the probability of Sn being less than t being less than Sn plus 1, and somehow, let's say if I gave you the joint PDF of Sn or Sn plus 1, would you be able to evaluate this probability? Okay, so once again, if you were given the joint PDF of Sn and Sn plus 1, remember these are two random variables. If you were given the joint PDF of these two random variables, would you be able to find this probability that you see on the screen? The probability that Sn is less than t is less than Sn plus 1. So there's a certain region in the two-dimensional plane that you want to find the probability of. Right? How would you do that? Kyun, Isha? You had the joint PDF.
Sir, law of total probability, sir.
No, if I give the joint probability, let's say some genie tells you what the joint probability is, and you just need to evaluate this probability. What do you do? What's random here and what is not random? Okay, so when I said, remember, I said we're going to build up on top of the things that we've done already. So it's very, very important that you really grasp the initial things that we did, right? This was a long, long time ago. Or यहाँ पे आके it's really essential that those concepts are very, very clear, right? So if you're clear about two random variables, this should be a piece of cake, right? So this is just an integral, a double integral. Double integral over what region? Over that region which satisfies this condition, that Sn is less than t is less than Sn plus 1. And what do you integrate? You integrate the joint PDF. So this is f of Sn, Sn plus 1, and these are small s's, Sn plus 1, and you integrate over this plane, over dsn and dsn plus 1. That's all you need to do. Okay? All right. So if I have this plane here, right? It's a two-dimensional plane, which is Sn here and Sn plus 1. Can Sn and Sn plus 1 ever be negative? Jimosen?
No, sir.
Why can it?
Sum of times.
Can you say again?
Sir, sum of time है तो वो negative नहीं हो सकता.
And times are not just any times. Times are exponential random variables, and exponential are always non-negative. Okay, so it's a sum of non-negative random variables. So therefore, it must be non-negative as well, right? So we're only looking at the first quadrant, therefore, right? What does this condition translate to? I mean, what is the area that I need to integrate over in this two-dimensional plane? T, remember, is a constant. T is a positive constant, right? Time t is positive, okay, or non-negative rather. So what area am I integrating over when I say okay, Sn must be less than t and t must be less than Sn plus 1? So, I mean, somebody else other than Mohsen, I mean, Jiva Saifa.
Sir, could we say that Sn is less than Sn plus 1 minus t?
Okay, that is going to make your life a lot harder. But you can say that. Because there's a much easier way to look at it. Isha?
Sir, we could actually draw a linear, a straight line, and we could say that the region under that straight line is where Sn is less than Sn plus 1. And that line would be equal to Sn is equal to Sn plus 1. Like a
So once again, you're all missing the point here. Right? So this is equal to what? Sn is less than t, intersection with t is less than Sn plus 1. Right? So this is actually an intersection of two events, right? That Sn has to be less than t and t has to be less than Sn plus 1, which basically means here Sn has to be less than t and Sn plus 1 has to be greater than t. Now tell me what I'm integrating over. So let's say this was some t. This is some t here and this is some t here. What am I integrating over? What area am I integrating over? Jimosen?
So the area above t on the y-axis and below t on the x-axis.
Below t on the...
So the upper left.
Yeah, that's fine. So less than t on the x-axis, greater than t on the y-axis, right? And that's what you integrate. That's simple. That's shouldn't be that hard, right? So this is what you're integrating over, and then there's a t here. So this is the area you're integrating over. And that's it. Okay. Right. So let's see. Try to do that. Split that integral. So integral जो है Sn plus 1 goes from where to where? T to infinity. And what about Sn?
0 to t.
0 to t, right? So I'm going to integrate over Sn first. So Sn 0 to t, and then this is from t to infinity, and then this is the joint PDF f Sn plus 1. This is small sn plus 1, and this integral is over Sn plus 1, and this integral is over dsn. Because the outside integral is over Sn, the inner one is over Sn plus 1. Okay. Now, So it turns out that this joint PDF can be found by looking at conditionals. And so this is 0 to t. This is t to infinity. And let me just split the joint PDF like this. So this is Sn plus 1 given Sn. This is Sn plus 1 given Sn times f of Sn times dsn plus 1 to dsn, right? And therefore, this is equal to integral from 0 to t, and this is t to infinity f of Sn plus 1 given Sn plus 1 given Sn, and let me pull up the dsn plus 1 here. Okay, so therefore this is one integral, and once I computed this integral, I can then just multiply it with f of Sn dsn. Okay, so far so good. So what do I have here? So this is the integral from 0 to t. What do I have inside the white brackets? What I have inside the white brackets is just simply the probability that Sn plus 1, the random variable Sn plus 1, is greater than t given Sn. Does that make sense? And this is times f of Sn times Sn. So this thing inside the white integral is just simply the probability. So this thing here is this probability. Okay. Now what I need to do is just try to compute what this probability is. So what is the probability that Sn plus 1 is greater than t given Sn is? So this is equal to the probability that Sn plus Tn plus 1 is greater than t given Sn. Right, so this is equal to the probability that Tn plus 1 is greater than t minus Sn given Sn. Okay, any questions here? And then I claim that there's since Tn plus 1 is independent of Sn. Why is it independent of Sn? Why is Tn plus 1 independent of Sn? Can somebody make an argument for me why that is true? Isha?
Sir, to start off with the problem, you stated that it's an IID.
Yeah,
so,
but if it's IID, तो Sn or Sn plus 1 independently होने चाहिए, तो फिर वो क्यों
so
independent?
sir, that's the same relation that we have for T as well, because Tn plus 1 is related to Sn plus 1.
You see, the IID जो है T's IID हैं. If T's are IID, S's are not IID. If that's what you're thinking, तो try to remove that misunderstanding. If T's are IID, S are not IID. S1 is not independent of S2. Similarly, S2 is not independent of S3. S1 is not independent of S3 because S3 में जो चीजें मिलके बनी हुई हैं वो S1 का भी हिस्सा है. Right? The same things make up S1. So there's a common element between S1 and S2, and there are common elements between S2 and S3. Right? Therefore, there is statistical dependency between the two. Right? What I'm saying here is different. I'm saying that Tn plus 1 is independent of Sn. Why is that? Ji Mohsin?
So because Sn does not include Tn plus 1.
Exactly, right? So because Sn is actually equal to T1 plus T2 all the way up to Tn, and that's where it stops. That's where it stops. It does not include Tn plus 1. And since T1 is independent of Tn plus 1, T2 is independent of Tn plus 1, and all of these T's are independent of Sn plus 1, Tn plus 1, their sum will also be independent of Tn plus 1. Okay, so that's an argument that I'm going to make, right? So the conclusion, therefore, is that since all of the random contributions in Sn are due to random variables that are all independent of Tn plus 1, therefore Sn must be independent of Tn plus 1 as well. And because of independence, I can conclude, so because of this independence, what we have is, what can I say about this probability, therefore? Agar Tn plus 1 is independent of Sn. क्या ख्याल है? What can I say about the probability? जी माज?
सर फिर कंडीशनल नहीं होगा, मतलब हम
Exactly. I can get rid of the conditioning. Minus small sn given Sn equals small s. Asal matlab iska ye hai, just to clarify, right? So therefore this is equal to the probability that Tn plus 1 is greater than T minus small sn, right? So the small sn is not random anymore because I have a conditioning there, right? Condition that I know that the realization of capital Sn is equal to small sn, okay? So this small sn is nothing but a constant. Small sn is nothing but a constant, okay? What is this probability equal to? How can I value this probability? I mean, is it easy? Is it hard? Ji Ghazi, what do you think? What should this probability be equal to? I mean, is there information given to us that will allow?
हम T की probability distribution को integrate.
Yeah, and what is the probability distribution? That's an exponential distribution. Okay, Maz, do you want to say something?
नहीं सर, ये कहना था.
Right, so this integrating from T minus Sn to infinity of what? Lambda e raised to a minus lambda times x dx. I'm going to use a different variable than s so that there's no confusion. Okay, and this turns out to be equal to, you can do this integration, that turns out to be e raised to minus lambda t minus Sn. Okay. So if this condition is 2, if this equation is 2, so putting this back to 2 into 2, what do I have? The probability that there are n switches. And I mark this 2 because I may need equation number 1 at the top. I may or may not, but nevertheless, so let's just keep it at 2. So there are n switches in this interval, 0 to t. This is equal to integral from 0 to t and probability that Sn is greater than t given Sn is something that I've found out already, right? This is lambda e raised to power, minus lambda times t minus Sn. And then I need the PDF of Sn. So this is something I still need to evaluate, right? So let's say this is equation number 3. Okay. So Sn is what? Sn is T1 plus T2 all the way up to Tn. So what is Fsn of Sn? Right? What is the PDF for this? How would you evaluate this PDF? I'm not going to do it here. I'm just going to give you the result. But I just want to see कि जी करेंगे तो किस तरह करेंगे? जी शोएब.
सर convolution लेकिन n times वाली वो convolution.
Exactly. So you would have to use n-fold convolution, and convolutions of what? Convolution of exponential PDFs. And that's actually an end of chapter problem that some of you hopefully would have done already, right? So I did not assign that as a homework this time around, I think, but it is an end of chapter problem. So you do an n-fold convolution of exponential PDFs, and the answer that you're going to get is actually gamma distribution, right? And the result is lambda raised to power n s n raised to power n minus 1 divided by n minus 1 factorial times e raised to power minus lambda. There's something missing here. I think there's a, yeah, so there's a lambda s n. Okay. And the way you go about this is using n-fold convolution. Why? Because t's are all independent. Okay. So once again, putting this back, in 3, what we get is the probability that you have n switches in this interval 0 to t is an integral from 0 to t e raised to power minus lambda t minus sn times all of this thing, lambda n sn raised to power n minus 1 e raised to power minus lambda sn divided by n minus 1 factorial dsn, and you integrate this, and lo and behold, what it turns out to be is a Poisson PMF divided by n factorial. So this is something I leave for you to verify. That should be quite straightforward, right? So this is an important result. The number of switches that you're going to get in a certain time interval follows a Poisson PMF. Okay, when the arrival times, or I would say the arrival times, the T1, T2, are all exponential and independent exponential and identically distributed, IID exponential. Okay, that's when the number of switches in a certain time interval is Poisson distribution, is a Poisson PMF, the mean of which depends on T, right? So that's also important. The mean of which depends on T. The larger the T is, the higher the mean. Lambda T, remember, is a Poisson PMF, mean of a Poisson PMF, a Poisson random variable. The larger the T is, the larger the time interval is, the greater the average number of flips that you can experience. And that makes sense. That's intuitive. That's very, very intuitive. Okay. It's just that the mean is linear in T, right? So that's one of the conclusions of everything that we've done. Okay. All of the things that we've done here so far. So the probability that there are n switches in 0 to t is equal to this, and this is a conclusion that all of this TDS analysis has led to. Now we don't have what we wanted, right? What did we want in the first place? So what did we want in the first place? We wanted, yeah, what is the probability that x of t equals 0? What is the probability that x of t equals 0? And we said this is the probability that they are even switches. Actually, when I say switches, this is, I think I used flips earlier, right? So switches and flips are, I'm using them interchangeably. Even switches in this interval, this is just summation n over even values, lambda t raised to power n e raised to power. So this is lambda t raised to power n divided by n factorial e raised to power minus lambda t. And how would you do the summation? This was one of the homework exercise. I think that was for a binomial distribution though. This is for a Poisson. How would you do it? Okay, so I'm not going to tell you. I'll let you explore this on your own because this was a homework exercise. So this turns out to be equal to half plus half e raised to the power minus 2 times lambda t. Right, so this is the probability that x of t equals 0. And therefore, the probability that x of t equals 1, what is that equal to? Quickly, this is just 1 minus that, right? So therefore, 1 minus that is half minus half times e raised to the power minus 2 times lambda t. Right, so this is the final result. Okay, there are certain things you can say about this result. What happens to this probability when t is small? So what happens? Nazish, when t is small, what happens?
E to the power minus 2 lambda t equals 1 और probability of x of t equals 0 is 1 क्योंकि वैसे भी वो जब start होता है it's
Right, good.
at time equals 0 it starts with x of t equals 0.
So when t equals small, the probability that x of t equals 0 is high. Right, so that's a rough conclusion that I can make. Is higher than the probability that x of t equals 1. And does that make sense? That should make sense. Why should it make sense? Because when t is small is actually when t is close to 0. When t is actually equal to 0, as Nazish said, the probability that x of t equals 0 becomes equal to 1, and the probability that x of t equals 1 that becomes equal to 0. Why is that? Because we start out with the initial condition being that x of t equals 0. Okay, that's our initial condition. Okay, and as if t stays close to 0, it's very, very small, the probability of x of t being equal to 0 is still very high compared to the probability that x of t equals 1, right? So and one keeps on, as t keeps on increasing, the one keeps on decreasing, the other one keeps on increasing. Okay, and that's something you can show. And there's one of them is a monotone, and then the other one is also monotone. Right? Until, and the saturation point, when t goes to infinity, what happens there? When t is large, Jimosin.
So both outcomes will be equally as likely.
Both of them become equally likely, roughly speaking, right? So probability that x of t equals 0 is approximately equal to the probability that x of t equals 1. Right? Both of them become equally likely. And that makes intuitive sense as well, because as you keep on going further and further in the future, the effect of that initialization basically diminishes. And one becomes as likely as being equal to 0, as being equal to 0. Okay? This would not have been the case. This would actually be the opposite case had I started out with x of t equals 1. And I could have done that. I could have played around and said, what if x of t was equal to 1? As x of 0 was equal to 1 as the initial starting point. What happens to the PMF? The PMF would just simply be flipped. Okay? जो अभी x of t equals 0 would have become x of t equals 1 and vice versa, right? And I could have played around with so many other things. I could have said, okay, what if I flip a coin at the beginning? So that's something you could try to work on. So that's maybe a homework exercise for you. Okay, what if my initial condition was also random? I flip a coin with a probability equal, with a fair coin, which is heads with the probability equal half and tails with the probability of half, and I flip it. And if it's head, I start out with a 0. If it's tail, I start out with a 1. Okay, so the initial condition is also random. If that's random, can you determine the probability or the PMF of this random variable, of this random process? Okay, think about that, because you may need to use total log probability for that. And okay, so I leave that off as an exercise. Let me know if you have any questions regarding this particular problem. Right? So I know this was involved, but at the end of the day, all it uses is concepts that are actually pre-midterm. Okay? It's just a mapping of events. That's what it actually uses at the end of the day. Any questions here? Ji Mohsin.
सर मैं ब्रेक में थोड़ा सा गूगल कर रहा था, ये आरटीएस नॉइज हमने पहले देखा हुआ है सेमीकंडक्टर डिवाइसेस के अंदर.
Okay.
तो ये पॉपकॉर्न नॉइज क्यों कहते हैं होंगे इसको?
मुझे पॉपकॉर्न नॉइज का नहीं पता एग्जैक्टली पॉपकॉर्न नॉइज कहते हैं. शॉर्ट नॉइज इज समथिंग दैट आई एम familiar with, not the intricate details though, right? I know कि semiconductor में जो noise है, short noise है, that's modeled as this, and perhaps because of the reason, I'm not exactly sure, but perhaps because of the reason that when the electrons jump over that barrier, silicon barrier, so that is a cause of noise. And their jumping is maybe exponentially distributed. Okay, the time it takes for one electron to jump and between the next, that's exponentially distributed, and that is perhaps why this is a good model for that, for the short. And that's called short noise. Noise short में आती है.
Right.
ठीक है, वहाँ पे थोड़ा सा different. That's not flipping, लेकिन वो Mohsin. So semiconductor, remember, the noise is not really a flipping. कि जी पहले 1 था और 0 था. वो थोड़ा सा इसी से build up करते हैं. Okay, so
could you clarify that?
So there's an end of chapter section which is called applications, engineering application, which is short noise, and you see the same ideas there. Okay, when you time arrival आता है, so you don't flip, you actually add. Okay, why don't you take a look and then we can discuss it again.
Yes, sir.
Okay, I think it's the last section of the chapter 8. Okay.